Okay, so let's go through the exam here. We have dy dx equals natural log of y plus x squared, y of 0 equals -1. We're trying to see, does the existence and uniqueness theorem guarantee us a unique solution, why or why not? Okay, so let's label a few things here. First of all, I have this x0, y0 that's given to me over here. My x0 is 0, my y0 is -1. Okay, my f of xy is going to be the natural log of y plus x squared. Okay, and then I'm going to need the partial derivative of this as well, right? So if we take the derivative of ln, we just get 1 over what was ever on the inside times the derivative of the inside part with respect to y, and that's just going to be 1. So there we have it. Okay, now I have to look at the domain of these functions, right? Remember that the domain of the derivative has to be smaller than the domain of the original function, right? So in this case, we're going to have the same domain. Natural log of y plus x squared, right? That means that y plus x squared has to be strictly greater than 0 in order for us to take the natural log of it. Okay, so that means that y has to be greater than -x squared. So then the boundary of our domain would be y equals to -x squared, which would not be part of the domain itself because y would need to be greater than -x squared. We're not allowing equality there. So y equals -x squared, the boundary of the domain is not part of the domain. So I'll remember that when I draw the domain here. Okay, so here are some axes, x, y. Let's draw the boundary of the domain in green, remembering that it is not part of the domain, so I'm going to draw it as dashed. So here's y equals -x squared. Pretty much looks like that, right? Parabola pointing downwards. Okay, and then that separates the xy plane into two separate regions. We need to determine which region is part of the domain, which region is not part of the domain. So let's use some test points here. Okay, let's say we use a test point above on the y-axis and below on the y-axis. So we could use 0, 1. If we try that out, right, we'll plug it into our inequality over here. We see that we get 1 is greater than 0, sorry, -0 squared, right? But that's the same thing as saying that 1 is greater than 0, which is definitely true. So then this point right over here, 0, 1, is definitely part of the domain. So this entire region outside the parabola is part of the domain. Now let's try 0, -1. Plug that in. So then now we plug it into this inequality, we get -1 is greater than -0 squared. So that simplifies to say that -1 is greater than 0, which is definitely not true. So this part right over here, where we have 0, -1, right, that is not part of the domain. Okay, so we're not going to shade that region. Now, right, we go back to this problem here. We have dy dx is equal to the natural log of y plus x squared, y of 0 equals -1, right? Well, in order for us to apply the existence and uniqueness theorem to this initial value problem, we would need for this point to lie in the interior of our domain. And we just showed that it didn't lie in the interior of our domain. It lies outside of our domain altogether. Okay, so we could say, since f of xy is not continuous at 0, -1, we have that the existence and uniqueness theorem does not apply. Okay, and that's all I was looking for there. For problem 2, now we're using the special form of the existence and uniqueness theorem for linear equations, right? So we already have this linear equation here. I'm going to go ahead and identify my x0, y0 again. Right, so we have 4, 7. Because this is a linear equation, we have a p of x, which is x plus 3 over x minus 3, just the coefficient on y there. Our q of x is ln of x. Okay, and then we have to look at the domains for each one of these functions, right? So for p of x here, right, we can't divide by 0, so x cannot be equal to 3. So the domain is going to be -infinity to the 3, union 3 to infinity. Okay, for the natural log function, well, we can't take natural logs of negative numbers or 0, so then the domain for this is going to be 0 to infinity. Now we're ready to go ahead and plot the domains here on the same axes, right? So we'll put in all of our interesting numbers. Maybe 0 can go here, 3 can go here. Okay. we'll do the domain of p of x first in blue, right? And so that has a hole at 3. There's continuous everywhere else. Okay, good. And then the domain for q of x, we'll do that in green here. Okay, so q of x is just going from 0 to infinity. So it looks like that. Okay, and then we have to remember that our x0 is 4, so we'll do that in purple. So 4 is over here. And we're looking for the largest interval that contains this, right, on which both functions are continuous. So we can go all the way starting at 3 and go all the way up to infinity, basically. So the largest interval would be 3 to infinity. And that does that one. Okay, now we're going to solve this problem as a separable equation. So we need to divide by 1 minus y. So we get 1 over 1 minus y dy dx is equal to 1 over 3 plus x. And now we'll integrate both sides with respect to x. So when we do that, we get 1 over 1 minus y. The dx is canceled off on the left-hand side, so it's just the integral of this with respect to y. On the right-hand side, we get the integral of 1 over 3 plus x with respect to x. Okay, and then now we have to integrate this. The integral of 1 over 1 minus y is negative ln absolute value of 1 minus y. The integral of 1 over 3 plus x is ln of absolute value of 3 plus x plus c. And then now we got to solve for y, basically. So we'll multiply both sides by negative 1. Get ln of absolute value of 1 minus y is equal to negative ln absolute value of 3 plus x. Plus c and minus c are the same thing, right? Call it plus c1, where c1 is negative c if you want. Okay, now we'll do e raised to both sides, keeping in mind that this whole thing is in the exponent of e here. Okay, so on the left-hand side, I'm just going to get absolute value of 1 minus y. Okay, on the right-hand side, I have e to something plus something, right? So then that means I'm going to get e to the first thing times e to the second thing. Well, e to c1 is just another constant, which I'll call c2, right? And then e to the negative ln of 3 plus x, put it in the denominator, we get e and the ln cancel off. So there we have it. Okay. And then now we can drop the absolute value bars as long as we make c2 plus or minus. So we get 1 minus y is equal to c3 over 3 plus x. Okay. And if you left your answer like this, that would have been full credit. But you can keep going and you could solve for y in terms of x. All right, so we can subtract 1. We get negative y is equal to c3 over 3 plus x minus 1. You could even get a common denominator here. All right, this is the same thing as c3 minus 3 minus x over 3 plus x, right? And then so that's the same thing as having negative y is equal to, well, c3 minus 3 is just another constant. You call it c4 minus x over 3 plus x. And then we can multiply both sides by negative 1, and we get y is equal to c5 plus x over 3 plus x, where c5 is just negative c4. So you can have that as your final answer as well. So that's separable. Now let's do linear. First, we need to write it as a linear equation, right? So this is the same thing as 1 over 3 plus x minus y over 3 plus x. And then we have to get this on the other side of the equation. So we have dy dx, right? We're going to add y over 3 plus x. I'm going to write it as 1 over 3 plus x times y. And on the right-hand side, we have 1 over 3 plus x. Okay, so our p of x here is equal to 1 over 3 plus x. And our q of x is also equal to 1 over 3 plus x. Okay, next step is we got to compute mu of x, which is e raised to the integral of p of x dx. Okay, so that's e raised to the integral of 1 over 3 plus x dx. So that's e to the ln of absolute value of 3 plus x. And the e and the ln cancel off, and you get absolute value of 3 plus x. And we showed in class that these absolute value bars don't matter at all, that both of the equations that you would get from considering 3 plus x to be positive or negative come out with the same solution. So we'll just say mu of x is 3 plus x then. Now we have to multiply both sides of the equation by 3 plus x. So we get 3 plus x on the left-hand side, multiply that out. We get 3 plus x on the right-hand side, and multiply that out. So we're going to wind up with 3 plus x times dy dx plus, well, 3 plus x times 1 over 3 plus x cancels off, so I'm just left with y is equal to just 1 on the right-hand side. Now the left-hand side can be rewritten very nicely as the derivative of mu of x times y. Okay, you can use the product rule to verify that that's true, right? Leave the first alone, take the derivative of the second, you get this. Plus, now you take the second, you take the derivative of the first and leave the second alone, you just get 1 times y, which is this. Okay, so then now we get that 3 plus x times y is equal to the integral of x, of 1, so we get x plus c. Now divide by 3 plus x, and we get y is equal to x plus c over 3 plus x. All right. Now let's try solving it as an exact equation. I'm going to start off by cross multiplying here. So when I do that, I get that this is 3 plus x times dy is equal to 1 minus y times dx. Now I'm going to subtract this over on the other side of the equation. So I get y minus 1 dx plus 3 plus x dy is equal to 0. So then my m of xy would be y minus 1. My n of xy would be 3 plus x. And then the partial derivative of m with respect to y would be 1. The partial derivative of n with respect to x would also be 1. So this is exact, okay? Because you get the same thing for the partial derivative of m with respect to y as you do for the partial derivative of n with respect to x. But now that we have that, right, we can say, thus, there is some function f of xy such that two things have to happen. The partial derivative of f with respect to x has to be equal to m, okay, and the partial derivative of f with respect to y has to be equal to n, okay. So using the fact that the partial derivative of f with respect to x is equal to m, we could say that f of xy is equal to the integral of m with respect to x, right? So that's just going to be the integral of y minus 1 with respect to x. So then we're going to get that that is x times y minus x plus arbitrary constant term, remembering that if we're integrating with respect to x, our y terms are constant then. Okay. Now, using the fact that the partial derivative of f with respect to y is equal to n, we could say that the partial derivative with respect to y of, well, here's our f, xy minus x plus g of y. So that partial derivative has to be equal to whatever n is, which is 3 plus x. So we take the derivative with respect to y of this thing, and we get x minus 0 plus g prime of y is equal to 3 plus x. All right, we get a little bit of cancellation here, right? So then g prime of y is just equal to 3, which means that g of y has to be equal to 3y. So now we can update what our f of xy is. F of xy is now xy minus x plus g of y, okay? And then our final answer is we have to set this equal to a constant. So we have xy minus x plus 3y is equal to a constant. Okay. You could leave your answer like that, or you could solve for y in terms of x if you want to. If you did that, we could factor a y out of these two terms. And we get x plus 3 times y is equal to, just add x to both sides. We get c plus x. Divide by x plus 3, and we get y is equal to c plus x over x plus 3, like so. Okay. Now let's find a special integrating factor for this non-exact differential form here, right? First, let's show that it's not exact. So our m of xy is equal to 3y plus y squared. Our n of xy is equal to 6x plus 3xy. Do the partial derivative of m with respect to y, right? And we're going to get that this is 3 plus 2y. Do the partial derivative of n with respect to x, and we're going to get that this is 6 plus 3y. Okay. And we see that these are not equal to each other, so they're not exact. Okay. So now we have to find a special integrating factor. Okay. So the special integrating factor formulas are on the first page of the exam over there. Basically, we need to find dm dy minus dn dx, right, over m, right? And if this is purely a function of x, then we're good. So let's go ahead and plug in what we have here. dm dy is 3 plus 2y minus dn dx is 6 plus 3y over m, which is 3y plus y squared. Okay, let me just make sure I'm using this correctly here. Oh, no, it's supposed to divide by n. I knew something was wrong there. Okay, so let's go back down here. Supposed to divide by n here. My mistake, everybody. So when I divide by n, this is going to be a 6x plus 3xy. Okay, so let's see what we get here. Up top, we have 3 minus 6 is negative 3. 2y minus 3y is negative y. So we have negative 3 minus y. Over downstairs here, we have a 6x plus 3xy. We could factor out a 3x from that. And when we do, we're going to be left with a 2 plus a y left over, right? And so this is negative 3 minus y over 3x plus times 2 plus y. And this doesn't really simplify very well to just be a function of x. So okay, so then now let's try the other way, which is dn dx minus dm dy over m instead. Okay, now the numerator is just the negative of the old numerator, right? Yeah, I just reversed the order there, so it's the negative of it. So our numerator will just be 3 plus y. Okay, our m is supposed to be 3y plus y squared. Okay, so I can factor that a little bit. Pull out a y downstairs, and now I have a 3 plus a y. So now I have common factor with the numerator and denominator, so that's going to cancel off. So I'm just going to be left with a 1 over y. So then I do have a special integrating factor because this is purely a function of y. So then mu of y is going to be equal to e to the integral of this thing, which I'm calling b of y. B of y dy. So that's e to the integral of 1 over y dy, which is just e to the ln of absolute value of y. The e and the ln cancel off. You get absolute value of y. And as we said before, we can drop the absolute value bars. Okay. So now that I have my mu of y, now I'm going to multiply both sides of the equation by my mu of y. So I'm going to take this equation and I'm going to multiply it by y all the way through. So I'm going to have the 3y squared plus y cubed times dx plus, let's see what I have for my dy here. I have a 6xy plus 3xy squared. dy. Okay, so then now we're going to show that this new differential form is exact. So my m is 3y plus y cubed. My n is equal to 6xy plus 3xy squared. My dm dy is going to be equal to 3 plus 3y squared, right? And my dn dx is going to be equal to, I think I might have done something wrong here. Let me make sure here. So I multiply by y. Oh, so I multiply by y, I get 3y squared. Ah, okay, gotcha. Sorry, this is a 3y squared here. So when I take the derivative, I should get 6y. My mistake. Okay, and then over here, when I take the derivative with respect to x, I'm going to get a 6x plus, take the derivative with respect to x here, I get a 3y squared. So I get a, 6y plus 3y squared. There we go. So this is exact, okay? And that's the end of that one. Now for the last one over here, right, we're just trying to express it purely as a function of y over x, right? So that's not too bad, right? I'm just going to take and I'm going to multiply the numerator and the denominator by y over x. Oh, sorry, by 1 over x, my mistake. 1 over x divided by 1 over x. So when I do that, I get that dy dx is equal to, well, 5 times y over x. Okay, minus the x's cancel out there, so it's just going to be minus 2 over 3 times y over x plus the x's cancel out there, so we're just going to get 1. All right, and then that's all I wanted for part A. For part B, right, now we're going to let v equal to y over x, and I'm going to find dy dx in terms of x and v. So using this equation that y is equal to xv, I'm going to take the derivative with respect to x on both sides. I get dy dx is equal to v plus x times dv dx using the product rule. And there we have it, right? That's all I wanted for part B. Now we're going to perform the indicated substitutions and rewrite the ODE as a separable equation. So we're going to take our dy dx here, we're going to replace it with what it's equal to. We got v plus x dv dx. And on the right-hand side, we have 5 times v minus 2 over 3 times v plus 1. Okay. And then now we want to write it as a separable equation. So I'm going to subtract v over. So I have x times dv dx is equal to 5v minus 2 over 3v plus 1 minus v. And now I'm going to divide by x, and I get dv dx is going to be equal to 5v minus 2 over 3v plus 1 minus v times 1 over x. Okay, same thing as dividing by x. And there we have it. Last thing here is the Bernoulli equation. So this one, I didn't have you guys do in class, so I won't go through it right now. Actually, you know what? Maybe I will go through it right now. So this says let v equal to y to the negative n, but really we want y to the negative n minus 1 or negative n plus 1. Okay. So if we do that, right, then now we can compute dy dx using the chain rule. So dv dx would be equal to, take the derivative of this, right, and we get a negative n, I'll write it this way, negative n plus 1 times y to the negative n. Okay, so that's the derivative of the outside function, but now we have to use implicit differentiation to say that this is multiplied by the dy dx, or, chain rule. Okay. All right, so now that we have that, it would probably help us to divide by this constant out front. So y to the negative n times dy dx is really the same thing as 1 over negative n plus 1 times dv dx. All right, now we're going to multiply both sides of the equation by y to the negative n. So we're going to get y to the negative n dy dx here, right? Plus sine of x times y to the negative n plus 1 equals cosine of x to the, oh, and I forgot to say what n is, my mistake. Since we have y to the fifth power, our n is equal to 5, right? So if I multiply by y to the negative n, this is going to be gone here. Let me go ahead and plug in my n equals 5 over here as well. So we have y to the negative 5 dy dx plus sine of x times y to the negative 5 plus 1 is negative 4, okay, cosine of x. And then over here, right, plug in n equals 5, we're going to have y to the negative fifth dy dx is the same thing as 1 over negative 4 dv dx. So then now I can make these substitutions in here, right? This term right over here is just negative 1/4 dv dx, okay? And then plus sine of x times, well, y to the negative fourth power is the same thing as my v, right? So this is y to the negative fourth. Okay, so that's my v. And then on the right-hand side, that's equal to cosine of x. There we have it. That is a first-order linear equation.